Welcome to the video presentation of the paper entitled Approximating Maximum Integral Multiflows on Bounded Genus Graphs. This is joint work with Chien-Chung, Mathieu, and Vygen. This work aims to extend previous results for the maximum integral multiflow problem on planar graphs to higher genus graphs. The maximum integral multiflow problem is a generalization of the famous edge disjoint path problem. In the edge disjoint path problem, we are given a supply graph G and a set of demand pairs H. The goal is to compute a family of edge disjoint paths connecting a maximum number of demand pairs. The maximum integral multiflow problem arises when the edges additionally come with integral capacities. The constraint being here that for any edge, the number of paths of a solution that contain this edge must not exceed its capacity. To simplify, we will focus in this talk on the case of unit capacities, so the edge disjoint path problem. The decision version of this problem is one of Karp's original NP-complete problems, and it is even hard to approximate. Even in the case when the supply graph is planar and subcubic, one cannot opt for an approximation ratio smaller than the lower bound obtained by Shudzoi, Kim, and Nimavat. One other difficult aspect of this problem is that the integrality gap of its natural LP formulation can be as large as the square root of the number of vertices. This last bound is also the best known approximation ratio, even when the supply graph is planar. At first, these lower bound results appear to me as a surprise. In general, all natural problems on planar graphs that I encountered before almost always had very good approximation algorithm, often constant approximation algorithm or PITAS. But then I realized that I was missing one aspect of the difficulty of the problem. The way demand pairs are disposed in the supply graph really matters. A natural question came to us: can we obtain good approximation algorithms when the demand pairs are disposed in the supply graph in such a way that altogether supply graph plus demand edges form a planar graph? This setting where G plus H is planar has been investigated before, but as far as we know, never in the context of approximation. For instance, Seymour proved that when G plus H is planar and Eulerian, that is when all vertices have even degree, then a simple necessary condition of the existence of a family of edge disjoint paths connecting all terminals, sometimes called the cut condition, is also sufficient. It was also proved that the problem remains NP-hard when G plus H is planar. Recently, we answer our question by designing a constant approximation algorithm for the maximum integral multiflow problem, and thus also for the edge disjoint path problem, in the case when G plus H is planar. This result was proved at the same time and independently by Garg, Kumar, and Shebo. In both papers, the algorithm worked by rounding integrally a fractional multiflow. The goal of the present work was to extend these results to the more general case when G plus H can be embedded in a higher genus surface. But before presenting formally our result, let me give you a short recap of some basic notions related to graphs on surface. So we can view a surface as a space where around every point there exists an open neighborhood that is homeomorphic to a disk. Sphere and torus are examples of surfaces. Those two have the property that they separate the 3D space into two connected regions, inside and outside. We say that they are orientable. However, not all surfaces have this property. Non-orientable surfaces include, for instance, the Klein bottle, or the real projective plane that can be imagined as a disk where two opposite points on the boundary of the disks actually correspond to the same point on the projective plane. If we have two surfaces, we can obtain a third surface by constructing their connected sum. We remove a disk from each surface and glue the boundary of this disk together. It turns out that any orientable surface, apart from the sphere, can be obtained as a connected sum of G tori, where G is called the genus of the surface. Moreover, any non-orientable surface corresponds to the connected sum of some projective planes. In this paper, we only focus our attention on orientable surfaces. And we will say that a graph has genus G if it can be drawn on a connected sum of G tori without edge intersections. In particular, planar graphs are the graph with genus 0. Remark that any graph can be embedded in an orientable surface with sufficiently high genus. To see that, you can draw your graph on a sphere, and in every place where two edges intersect, you add a handle onto the surface. Each operation will increase the genus of the surface by 1 and decrease the number of intersections by 1. The genus is somehow a measure of the complexity of a graph. The main result of the paper that I'm going to prove in this talk is to show that for instances where G plus H has genus at most G, there exists a polynomial time algorithm with approximation ratio big O of G squared times log G. Since the upper bound on the optimal integral solution used in this algorithm is the value of the optimal fractional solution of the edge disjoint path LP, we even obtain that the integrality gap of the edge disjoint path LP is also upper bounded by the same constant. Using a result of Tardosh and Vazirani, our theorem implies an approximate max flow min cut theorem. For a comparison, without any assumption on G plus H, this ratio can be as large as the number of demand edges, even when the supply graph is planar. So given an input graph G plus H, we will denote E, it's the supply edges, and D, the demand edges. We can assume without loss of generality that G plus H is connected. Otherwise, you can apply the algorithm on each of its connected components and return the union of the solutions. We define a D cycle as a cycle in G plus H that contains exactly one demand edge, and we denote by C the set of all D cycles in G plus H. With this, the edge disjoint path problem can be formulated as follows. Find a subset of edge disjoint D cycles with maximum size. You will see later that it's convenient to work with cycles because set of cycles on surfaces have a lot of interesting properties. Let's now look at the fractional relaxation of this LP, where here D cycles can be selected fractionally. Given a feasible fractional solution f of this LP, its support will refer to the set of all D cycles that have positive value. To compute an integral solution of the edge disjoint path problem, we will first compute an optimal fractional solution. Then we will simplify the solution by getting rid of unnecessary crossings. During this uncrossing step, we will only lose an epsilon fraction of the value for an arbitrary small epsilon. Then the algorithm distinguishes two cases. The first case is when at least half of the value of the fractional solution is on separating D cycles, whereas separating cycles are the ones that separate the surface into two connected components. For instance, any cycle embedded in the plane is separating. This is the Jordan curve theorem. This branch of the algorithm we'll construct another integral solution whose support contains only separating cycles, and whose size is at least the value of the maximum fractional solution divided by square root of g. Not surprisingly, this branch of the algorithm follows a similar strategy as in the planar case. On higher genus surface, however, they can be cycled, like C in the bottom right figure, that when we cut the surface along those cycles, we do not disconnect the surface. In this second case, we will thus consider the case when at least half of the value of the flow is contributed by non-separating cycles. We will construct here another integral solution whose support contains only non-separating cycles and whose size is at least the value of the maximum fractional solution divided by big O of g squared times log g. In particular, this case appears as the bottleneck in the overall approximation ratio. I will now give details of each of these steps one by one. First, we compute an optimal fractional solution f star of the edge decision path linear program. Notice that the number of variables of this LP is exponential. Fortunately, there exists an equivalent formulation that uses flow conservation constraints for each vertex and has polynomial number of variables and constraints. Therefore, we can compute an optimal solution in polynomial time, and then by some classic flow decomposition techniques, we can obtain an optimal fractional solution f star to our original LP, whose support has polynomial size in the input length. Then we uncross this flow f star to obtain another fractional solution f bar that has roughly the same value and such that any two cycles in the support of f bar cross at most once. This property will be useful later in following steps of the algorithm. Intuitively, when two cycles C and C prime in the support of f star crossed at least twice, we pick two consecutive crossings and exchange the two portions of the paths between the crossing points. After this operation, the number of crossings between C and C prime has decreased by 2. We will repeat this operation until any pair of cycles cross at most once. Although this procedure looks very simple, analyzing it and proving that the total number of uncrossing operation is polynomial is surprisingly tricky. The difficulty comes from the fact that cycles have fractional weight, and the uncrossing operation must take the weights into account in order to keep the solution feasible. We must also be careful with the position of the demand edge on each D cycle, otherwise we might create some cycles with with 0 or more than one demand edge. Also, uncrossing two cycles might create new crossings with other cycles. If you are interested by the details of this uncrossing step, you can look at the section 4 of the paper. At this stage, we obtain a fractional solution f bar, which is minimally crossing. Now we look at the value of the flow held by separating D cycles and assume in step 3 that this corresponds to at least half of the value of f bar. We will construct an integral solution in two steps. First, we compute an half integral solution, and then we will use this half integral flow to obtain an integral solution. To obtain an half integral solution, we first remove all the cycles in the support of f bar we remove all non-separating cycles in the support of f bar while losing only a factor 2 in the value. Then we will combine the fact that on a surface, two separating cycles must cross an even number of times with our property that cycles cross at most once to attest that no pair of cycles cross. This implies that such cycles have a laminar structure. If we look at the parts of the surface lying inside these cycles, they have the property that the symmetric difference of any two of them is empty. Now we use the result of Ga, Kuma, and Shebo to compute a half-integral solution whose support contains only separating cycles and size is at least a constant fraction of the optimal fractional value. To obtain such a half-integral multiflow, intuitively you can imagine that we orient each cycle clockwise, and for each edge, we allow a flow of value 1 in each direction, thus allowing congestion 2 per edge. It turns out that this new problem with congestions admits LP formulation whose matrix is totally unimodular, and which therefore admits an optimal solution that is integral. Then we obtain a feasible half-integral solution to our original problem by dividing all the flow by a factor 2. I invite you to have a look on the paper of Ga, Kuma, and Shebo if you are interested by the details. You can also see our previous paper on planar graphs for an alternative combinatorial algorithm. From this half-integral solution, we now construct a set of edge disjoint paths. Notice that even though the cycles in the support of F-half do not cross, we may still have some edges shared by several cycles. Notice also that it follows from the half-integrality that an edge can be shared by at most 2 cycles. We construct a graph I that has one node for each cycle in the support of F-half, and such that 2 cycles C and C' are adjacent if they share an edge, a supply edge. To obtain an integral feasible solution, our algorithm, the goal is thus to find a large independent set in this intersection graph. Fortunately, using the fact that G plus H has genus G, we show that this intersection graph can also be embedded in a surface of genus G. And in particular, we know from a theorem of Ewood that such a graph always has a node with degree at most roughly square root of G. This implies that we can use the classic greedy coloring algorithm to compute in polynomial time a proper coloring of I with at most big O of square root of G colors. The largest class in the largest color class is a feasible solution to the edge disjoint path problem. We can output those cycles. This finishes this branch of the algorithm. It remains to treat the case when most of the value of the uncrossed flow F bar is contributed by non-separating cycles. In this case, some cycles may cross each other exactly once. And unfortunately, the argumentation used in case 3 fails. To overcome this issue, we will pick one homotopy class of cycles in the support of F bar and remove all other cycles. We say that 2 cycles in a surface are homotopic if one can be transformed into the other by continuously moving it onto the surface. It is an equivalence relation, and those cycles on surfaces can be partitioned into homotopy classes. It was recently shown by Green that on a surface with genus G, a family of cycles that pairwise cross at most once can be partitioned into at most big O of G squared times log G homotopy classes. Therefore, there exists an homotopy class in the support of F bar whose total value is at least a big O of G squared times log G fraction of the total flow value. Since we can decide in polynomial time if 2 cycles are homotopic, we can compute this heaviest homotopy class in polynomial time. We can now observe that 2 homotopic cycles cross an even number of times, so after our uncrossing steps, they do not cross at all. In particular, non-crossing homotopic cycles can be nicely ordered. We can order them in such a way that the portion of the surface that lies between 2 consecutive ones is annulus. We can then use a simple greedy algorithm that considers the cycles in this order and iteratively adds a cycle to the solution if it is edge disjoint from any cycles in the current solution. We can show that this greedy algorithm returns a set of edge disjoint paths whose value is at least half of the total value in this homotopy class. Putting everything together, the size of this solution is at least a big O of g squared times log g fraction of the value of the optimal fractional solution. This concludes the description and the analysis of our algorithm. Can we improve further the approximation ratio? The following instance is inspired by a paper of Garg, Vazirani, and Yanakakis. Its supply graph is represented by black edges and has n concentric rings. There is one demand pair connecting each Si to Ti. And to not charge the drawing, I have represented only one demand edge. This instance has several interesting properties. First, the integrality gap of the edge disjoint path is n. Indeed, any 2D cycle must share an edge. So the maximum integral solution has only one path. Moreover, the fractional solution, there is a fractional solution of value n. Two commodities, they share a ring, and reroute one force in each direction. The total flow going through each edge is therefore at most 1, and this fractional solution is feasible. Then such a graph has genus at least n. This means that using the optimal fractional solution as an upper bound in opt, the approximation ratio must depend at least linearly in the genus of the surface. Finally, this graph can be embedded in the projective plane. This suggests that achieving a good approximation ratio for instances that can be embedded on fixed non-orientable surfaces using LP rounding strategy may not work easily. This leaves a first open question. What is the best approximation ratio achievable in polynomial time when g plus h is embedded in the projective plane? As far as we know, the best upper bound so far is the square root of the number of vertices, as in the general case. The second natural open question is whether one could improve our approximation ratio of big O of g squared times log g in the case where g plus h has genus g. Let me suggest one direction that already leads to an improvement ratio of an improved approximation ratio of big O of g squared, but may potentially improve it further. Notice that the bottleneck in the approximation ratio of our algorithm follows from the fact that in step 3', we removed all cycles except from one of the at most g squared times log g homotopy classes. To obtain an integral solution, we can actually run the final greedy algorithm on several homotopy classes as long as those cycles do not cross each other. This brings the following question. Let gamma be a set of simple curves on an orientable surface of genus G, such that any pair of curves in gamma are non-freely homotopic and cross at most once. Let G of gamma be the graph with vertex set gamma, and where two curves are adjacent if they cross. What is the best upper bound on the chromatic number of G of gamma? Any improvement on that question will immediately imply an improved approximation ratio for the maximum edge disjoint path and maximum integral multi-commodity flow problem when G plus H has genus G. As far as we know, the best upper bound on the chromatic number of G of gamma is big O of G squared. And it follows from the fact that this graph always has a node of degree at most G squared, big O of G squared. For further details on this question and the edge disjoint path problem on surfaces, I invite you to read our iCal paper, our journal version to appear, or even the last chapter of my thesis. Thank you very much for watching this video until the end.